Hey, and it's the go live or go barely alive. You know.
And Luca.
Hello, hello. Yeah, barely alive, but we made it. In fact, I will be off next week. So yeah, that was the goal for this week to get to the end of the week. No, I'm just kidding. But I'll be enjoying the lakeside from next week. That's very good. And it's been a couple of weeks that we have done our last episode. So how how have you been, Thomas?
Well, I've been at the lakeside already, so
Yeah.
the good news is that was good. The bad news is no more lakeside next week for me. But
Nice.
yeah, so
Okay. But
I
what
guess
did we talk about the last time? We talked about the LLM, among
right.
other things. There was a few things, and the LLM has one thing that does particularly well, and all inference frameworks, but for that matter, they need to be all inference frameworks that deal with autoregressive models like LLMs, because they need to keep track of not they make sure they don't do more work than they're supposed to. So whatever already happened in terms of computation, you don't redo it. And since the autoregressive nature of models shows itself in the attention, because you need to go back, all the rest of the model is concerned with a single token, a single floating point vector that can be traced back to a single token. And so it just transformations along this vector dimension, in this like multi-dimensional space that represents letters, words, concepts, ideas, whatever it is. Uh, and then all the MLPs don't see the sentence; they only see
Right.
the, and it's the transforms itself into a concept, because the deeper you go, the higher level probably you go. But the point is that at some point of the model, it's in the attention. You also look sideways and say, okay, like let me see how I can change myself. And the way I picture it is always, maybe it's completely bogus, but the way I picture it is that everything else, MLPs with their nonlinearities, is like folding this high dimensional space so that things are supposed to be close together. They're actually close together in a Euclidean sense. And but then when attention comes, the current location in this and multidimensional space changes, because you move you where you are according to a weighted average of where uh, uh, other things are in the sentence, in the sequence, sorry. And
Yeah.
so yeah.
So if you want, one of the things was previously we had the recurrent networks, the LSTMs, and
Yep.
those always like all the information you got from the previous step was encoded in the input, right? In the
Yep.
hidden state.
Yep. Yep.
And there was only like hidden state for any given point of time in memory, or
Yep.
maybe the next one too. Uh, but now with the attention, you can look back during
Yep.
the computation, right? So you
Yep.
don't you explicitly keep the state from the previous steps.
Yeah, and you can look back at any of the million tokens that precede you. So it's a long thing. It's a long operation you're making. Um, and one of the things that happen when you have uh, a new token in the attention is you take that, then you break it up into the heads, and then you multiply it by matrices that kind of project part of your embedding um, into being a key and a value for and a query for the matter, so that you can compute attention itself. So you compute attention not on the embedding associated with the token itself, not in the latents that represent your token, but on a byproduct of that is brought in by linearly projecting these things. And so you get these vectors, and then you need to compute attention. But of course, you can avoid doing all this computation because they are matrix, the matrix multiplication involved there. And you can avoid doing that for all the tokens in the million tokens that precede you if you'd already did that in the previous steps. And you need to do it across the model because there's an attention for each attention block. And so where we are going with this is that something that is well known as a name, the KV cache. What is the KV cache? The KV cache is basically all the already computed values of keys and values that you need to uh, combine with the query, which is only pertaining the next token, to obtain, well, first the attention weights when you combine keys and queries, and then the weighted average that you compute when you also then once you have the weights, then you multiply them by the values, and then you get the new the new contribution, the output of the attention for the next token. And all this process hinges on retaining all these things in memory. But this thing in memory grows over time because at the beginning there will be 0 KV cache, and then there's 1 KV cache, one element KV cache, and then 2 element, actually more elements, but in the sequence dimension is 1 and 2 and 3 and 4, according to how many things you already computed. Or if there's a prompt, there's a pre-fill phase where you do a computation all in parallel with a full sequence in input, and then you start generating autoregressively. And so in the pre-fill phase, you will populate all these key the key values, and if you store them, then when you need to generate the next token, you will already have them. You don't need to go back and recompute them, which is great, but you need to store them someone first. Second, this KV cache grows in time. So it grows, and things that grow means that they change their shape. And things that change in shape don't go well hand in hand with compilers. And so if you have a compiler sees a KV cache of length 100 along the sequence dimension, and then the next step it sees a KV cache of length 101 and 102, and that's not good because it will trigger recompilation every time, unless you can manage dynamic shapes. But even if your compiler manages dynamic shapes, things like CUDA graphs don't, and so you can go this far with dynamic shapes usually. And so you need to find ways to say, okay, let's turn this computation into one where there are no shapes changing. And instead of like changing a shape, you can pre-allocate a buffer and then use part of the buffer to say, okay, it's filled up until here and not until there. And so you keep an index where in the sequence dimension to say, okay, my KV cache is full up until 100, which is great, except that number cannot be an integer, because if an integer changes as an input to your computation, that you will also trigger a recompilation, which is something you want to avoid. So probably what you want to do is use a tensor to keep track of that value of that index, and so you can do that. And there's a few other things you can do, like for example, VLLM breaks up the KV cache into pages, and hence paged attention, and so you don't have to necessarily pre-allocate a contiguous amount of memory that stores all your million KV cache, or pre-allocates your million KV cache, but you can break it up and use it with a summing direction. Anyway, this is more or less what we're going to talk about today. And I don't know, Thomas, where is the best place to start talking about KV cache and how to make it compiler friendly? Because here, we're talking about compilation. So PyTorch Eager is not worried about shapes of things changing. So if you were just,
Right. I mean,
uh, yeah,
maybe you can draw a little thing where you show the KV cache
oh yeah,
and
let's
how
do
we
that.
need to push the data through it.
Okay, you will guide me through the drawing. So let's say we have our model, which has many blocks, right? And each block, ooh, sorry, I dropped my iPad pen and now I need to keep it perfectly orthogonal to the iPad. Otherwise, it won't work. I need to change the tip. Anyway, um, here's the model, and each of these is a block, a transformer block, and the transformer block has a few things that are MLP that go, let's say, element by element. They don't interact in the sequence direction,
Right.
and then there is attention. And attention is something that, in fact, needs some sort of, you either compute it or you retrieve from some place where you store keys and values. We can keep them separate conceptually, but they can be stored in a single buffer or not. And let's say we're computing token, well, the sequence n plus one position in the sequence, and we have already went through n in the sequence dimension. And so here will be in the MLP, we'll only compute like this projections for the n plus one token
Right.
only. We don't even see the history here. So if we have a sequence of many tokens here, I'm talking about tokens in a very broad term. I find myself talking about tokens, but they're not tokens. They're floating point vectors that represent something that is at that point.
Yeah.
But essentially, these things are like MLPs are unbothered by your n uh, floating point vectors. They're only bothered by what you're computing about the n plus one. So here, this is the only thing that will enter here.
So in other words, they're local in time, right?
Yeah, they're absolutely local in time. They have no indication that they understand anything beyond this next thing that we need to compute.
Right.
Uh, all the information is stored in the, let's say, in the embedding dimension. So how much, like in the 4,000, 8,000, whatever it is. And so the floating points here is for each position is what the MLP sees. But the point is, like, when you have the attention, then all these become very important, because attention basically will determine a weighted average between your n plus one and whatever else in the previous n. After, like, it's not really weight, well, it is a weighted average, but the way you compute weights of this weighted
Yeah.
average uses keys and query. The query is related to this one, and then what you average about is the values, so not the actual, like,
Yeah.
embeddings.
So the key, I guess, is that we need for this n plus first token, we
Yep.
need to go through all the previous tokens, and they will all have produced key vectors. And now we're taking the matrix that or the product of all the key vectors with the query vector,
Yep.
and from the n plus first token. And of course, the n plus first token itself has a key vector too. And so now we have like n plus one key vectors and one query vector. But so the upshot is that we computed the kn plus 1, the key vector for n plus 1,
Yep.
but we needed to remember all the old ones, right?
Yep.
And
We need to
so,
store the key i's and the i's. We don't need to store the query, but at each step we'll have a full set of key, value, and query for our next one. And so we basically stash the new ones, and we just put them back into some container that we can then use to retrieve the previous information and feed that to each. And this happens for each block, right? So you have an attention for each block, so each block will need to do this job of
right,
stashing stuff and recovering it. Then inference frameworks are usually good at having more tricks to say, okay, if I'm always using the same prompt to prompt the model, all the conversations I have will have the same keys and values at the beginning because I can just cache them across conversations, and this is where Page's attention and Radik's attention from SGLang do the work. They keep they address this KV cache in a cross conversation, cross inference uh, strategy with such a strategy so that you don't end up recomputing what you have already computed over and over. And you may not know it, so they kind of figure out what is similar with respect to what they have in the active cache. Anyway, back to here, we have this like place where we store keys and values, and different frameworks do it differently, right? And so again, in eager world, you could just store them as a buffer, and the buffer could grow. Except the fact that it's never good to make a tensor grow. It could create allocation problems. But in theory, if you're not concerned about performance, you can just say, okay, now my new tensor is one tad longer than the previous one. Compiler world doesn't like shapes that change.
right. So maybe we just look at some code, how we would
Yeah.
do it,
So
and
with
we
all this
can
in
see.
mind, let's start interpreting some code. Um, should we look into LGPT or something
Yeah,
similar or something else? What you prefer, whatever.
yeah. Maybe we start with legibity,
Yep.
and do you want me to show it?
Yeah, sure. If you want to do it, otherwise I can do it too.
Yeah. So
Whatever.
okay. So uh, I prepared. So here is the KV cache class, and before we look at the KV cache class itself, maybe we look at how it fits into the attention. So here's the MLPs, and here is the attention, and the attention is clearly, the attention forward is clearly too complicated. But yeah, what can you do? And so the key thing is that you apply the KV cache, and so basically you just say KV is self.kv cache of KV. And so all of this is a lie, if you want, because this K and V will be, after the prefill, it will be one element only.
Yeah.
And so those are one element, and those, in contrast, are the full sequence length. And the KV cache will do that for you. And then basically what you do is you feed it into the scaled dot product attention that we all know and love, and which is one of the kernels that has been optimized to great extent with the flash attention series, and also cuDNN has an implementation for it, and many others, Xformers,
Yeah.
many great.
Just to clarify, if you run up where you just were, it's
Yeah.
interesting to see where you multiply, where you obtain the K's and B's from the matrix multiplication with W K and WV,
Oh
just
yeah.
to clarify that aspect.
So basically, you have to chase it a bit,
Yeah.
but there is a linear layer called QKV
Yep.
that basically computes query, key, and value for the current position to be used in the
Yeah.
attention.
And this is
Uh,
for the current position, at position current.
yeah,
So here we're not seeing the history of anything. We're
right.
still happily computing our next token, and we're in next token land. And then and then we need to split it because uh,
Yeah, there is a thing called
application.
multi-head attention where you do this exercise, the attention matrices and stuff for multiple parts. You split the vectors in parts and treat them separately,
Yeah.
but that's all busy work and indexing.
Yeah, it
Uh,
doesn't
so
change the core of the thing. So what we learned is that we compute with through that KV, we compute the Ks and Vs and so on for the next token, and then we call into the KV cache to say, okay, given this is the current position, and this is my new K and V for the new token, return K and V for the whole sequence.
yeah, and so for LitGPT, and because obviously we do have a lot of opinions on what is idiomatic PyTorch. For LitGPT, KV cache is an NN module. There will be a submodule for the causal self-attention, which means it has the drawback that kind of you can only use the model for one like set of KV cache inference tasks at a time. But other than that, it works great. So the K and V are buffers, and basically the shape is given by the maximum sequence length that you want. You allocate that KV cache.
Yeah.
Um, and then you go, and when you get new K and V, basically what you do is you call an operation that is index copy in PyTorch
Underscore, which is
with
a big problem.
underscore, which is like the indication that it modifies its first input. And the first input is the K and V from the KV cache, the buffers that contain all the data. And then you add the positions given by input position, you put the K and V from the current computation. And so that's a neat trick.
And the
And then
BS, what is that BS?
hmm?
What is the BS?
The BS is the batch size. So when we implemented batched inference here, we wanted to have this thing dynamic in the batch size for because if you have here in the K, that will have a certain shape. And the deal with the index copy is that you need to match all the dimensions except the one that you're indexing. And
Yep.
we're indexing the sequence dimension, and all the others, including the batch dimension, need to match.
Yep.
And so this is indexing with the batch size. So I could pre-allocate a KV cache for like multiple
Mhm.
instances, let's say 3 or 8 or whatever. And then if I only have one thing that generates, I don't want to run the entire batch size through it.
Yep.
And so we index it here. It's a
Yep.
little optimization. And because batch size is something that is static, more or less, so if you have static shapes, then it's okay to index here.
Yep.
Um, and so this is in place, and then you return this thing. So the K that is passed in here, it gets switched for the self.k, or more
Mhm.
precisely, this self.k with the batch size, which is a view into the self.k buffer, right?
Yeah.
And then you return k and v that are now suitable for passing into the attention. And so the other thing that is interesting here and very idiomatic PyTorch is that the computation itself is in a function. And this is always something that PyTorch always does. You have the NN module interface, and then you have typically the forward of these modules more or less is take all the buffers and parameters and inputs and call a function in torch NN functional
Yeah.
on it. And this turns out to be a very good pattern also for compilation. And now we're back in the compilation regime. For compilation, now if Thunder wants to do fancy things, and it does want to do fancy things here, it can just redirect the batch index copy function here and do its magic there in
Yeah.
order to.
Yeah, because what is the problem? Like fundamental problem here is that we have an in-place operation, and we know that within the computation trace, Thunder, but also like in general, compilers have a hard time with in-place things because they are basically every compiler is ideally completely functional. It has in any line in any execution step, it will have inputs and then outputs that are distinct from the input. So it's easy to transform that computation. Whereas if you kind of overwrite some numbers in something that it was pre-allocated, then reconstructing the data flow is pretty interesting, and also you cannot reorder, you cannot easily figure out what to do. And so Thunder tends not to want to do that, although there's some support for in-place operations. But sometimes the way you treat in-place operations is not always efficient. But if you know what that operation is about, then you can be efficient about it. And so if you have the ability to write a Luca side that says, okay, when you hit on this thing, just do the other thing. Don't treat in place as you usually do, but do something that is more efficient. You can hand optimize that operation. And that makes a lot of difference because the KV cache is very large, is huge in memory. So you need to
Yeah.
make sure you're not kind of copying everything, creating another copy of something or something like that. So what do we do here in terms of like making it compiler friendly? Because that's what it's all about. How do we make something that we need to stash things into progressively compiler friendly?
Yeah, one thing is to just have this as a separate function. The other thing I want to point out here, this is not super compiler friendly. So as a convenience, when automatic multi-precision is used, we change the D type of the buffers by taking the buffers, calling to, and then assigning to the buffers again. And
Mhm.
this is supported in Thunder, but it's a bit tricky. And so the rule of thumb should be if you can, don't like change the buffers and parameters during the forward, right? If you want
Mhm.
to initialize your model, do initialize your model. If you want to do computation, do the computation.
Yeah, yeah.
And yeah, but things grow and you have to balance like perfect beauty
And
and
ugliness of
well
mixed.
and convenient sometimes.
Yeah, yeah,
Yeah.
of course.
Okay, so if we look at the recipes that we talked about a few episodes ago, we see that one of the most basic things here is that we redirect index copy, and I have to find it. Is it
Yeah.
here or is it in the? Probably it's in the transformers recipe. Okay, yeah. So here's the in-place index copy transform, which sounds really fancy. but it's just a little redirection for index copy. And basically what it does, it tells you in the meta function, and this is just a transform, and it registers a symbol and an executor, which are all things that we previously did, right?
Yep.
And so what it does is it mimics the index copy function, and then in the implementation, it just does the index copy, and this is an index in place index copy. And so what this does, it hides the in-place nature of the index copy here from Thunder, which is like a bit touchy, but it does work. And so this is what we do in order to do this. The other thing
Yeah,
that we
because
do,
just to reveal why this is important is that we basically hide it from Thunder. So we say don't worry about this being an in place because it basically we're writing on stuff that is free. Like we're writing on free space, and so there's no need to care about what was written before where we write because it was
yeah,
all initialized. So we're only growing there. Um,
yeah, and of course optimization is there in the sense that you have the formal description what you do, and you might step outside uh, what is you just have what is the common convention, but you have to make sure that the other parts of the system, they can still operate as they
yeah.
think it's good. And so this lets Thunder do its thing, and we take responsibility that everything's cool with the index copy. Um, and so the other thing we do here is that we add a tag that or that we replace the index copy from ThunderTorch, which is the out of place, that we replace it with the in place version again. It's not really rocket science, but this allows us to basically use the KV cache with the in-place functions without worrying about creating a copy from functionalizing the in-place operation.
Yeah, and this was in the Hugging Face Transformers recipe because Hugging Face Transformers have a similar way of handling the KV cache if you choose a static KV cache, right? It's
Yeah.
not exactly
So
the same because it doesn't use a buffer, but
yeah. So if you look at the transformers, they have their own page on the KV caching strategies, and you can see here that there's like a lot of things, and probably a lot of things will be coming to LitGPT as well. But so basically, one choice they have here is the dynamic cache and the static cache. They have a latency, which is interesting. But so what this does is the dynamic cache, it does the uh, it does the thing that you would intuitively do, and the LitGPT also does. If we go back to LitGPT, you saw that there is an option to in the attention. There is an option if you have this input pos max p, then it will cut the K and V that it feeds into the attention layer. And that, of course, makes it more efficient because if you don't do this, you will have like a long attention vector that it will read in, but it's all masked out at the end. And so
yeah,
with these days, in the olden days, you had attention length like 2K or so. That was the large context.
yeah,
But nowadays you have like a million, and
yeah,
then suddenly it's attractive. But so if you do it like this, suddenly K and V have a different length at every iteration. And this will trigger recompilations in Thunder, but also in other compilers like Torch compile will also recompile. And so the dynamic cache, what it does is it cuts this similarly. The static cache, on the other hand, this keeps it static, and what it does, it feeds like everything in the cache into the attention, and this is why it's high latency, because basically you you have a way too long cache that you feed in there, and this is where the next trick comes in, right?
Yep.
So maybe I stop sharing, and we will see if it keeps me.
Yeah. So well, what do you do? Like, where is the in between feeding a ton of things um, in the attention, even if you don't need that, and or growing the cache one by one and changing it at every iteration, right? There's
Yeah,
a like there's something you can do in between, right? So, because one thing is
yeah,
stupid from one point of view, the other thing is stupid for the other. What you could do, well, there are a bunch of things you could do. One thing you could do is say, okay, maybe I can keep the trace with static shapes for different amounts, like you quantize, like you pad up until some point and you say, okay, I'm keeping the cache and like
yeah,
1000, 2000, 4000, 8000 Fibonacci, whatever, and you go up.
right.
That's a kind of the first thing you might think about doing. The other thing is maybe you have some leverage and say, okay, maybe I can modify my attention kernel so that I can pass in some number that tells the attention, yes, of course, I provide you with a giant tensor, but just look, you need to go up to this because I'm communicating to you that the interesting thing is up until that point. But conventional kernels don't do that. Specialized kernels may do that. And so,
Yeah,
for example, we talked about VLLM with page attention. They have a special attention kernel. Um, and
yeah,
do you know about many implementations that like allow that?
yeah. So one thing we said is that you are not supposed to pass in an integer giving this cutoff length because that will trigger a recompilation.
Of course,
But
a
and it
raw,
had to,
a naked integer, like yeah, the
yeah, a
number.
Python integer.
Yeah, yeah, yeah.
And also, if you do if you want to do things like CUDA graphing things, then this will also like
Yep.
not be visible. Like you can vary it when you have a CUDA graph. But what you
Yes.
can do, of course, is you can pass a CUDA integer, a tensor,
Yep.
and uh, and then you go and you take, for example, we use Triton quite a bit. Triton has an example attention kernel. You can take that kernel and just add the parameter like max position, and
Yep.
then
Has a tensor.
yeah, and then you can just say if it's outside the max position, yeah, go away.
Yep.
Maybe you can do that.
Yeah, yeah.
But yeah, you can actually do that. And so that like does it fairly neatly. Um, for VLLM, they have a more elaborate scheme. They have a thing called paged attention, where they foresee not only that you have like varying length, but you also might have a cache organization where you have multiple batches, or where you have a batch size more than one, either from concurrent generation or maybe
Yep.
interleaved ones. Um, and so you don't know how much memory you will take, and so you go and have a paging system where you first say, okay, my page size might be 1000 tokens or a sequence length of 1000. And then you go and you allocate blobs of 1000. And then you can also pass a vector like with the page indices, right?
Yeah.
And if you have a this is not used page, then you can skip it in the attention.
Yeah, and the pages may not even be all like sequential in your organization. You could have like you could
Yeah,
store prefixes of different nature in different pages, and so you have a lot of flexibility. Basically, you're creating an indirection, just like the OS in the normal operating systems have, um, so that you can then reason about where things are in something that doesn't need to be contiguous but looks contiguous to the process. And then the kernel needs to be able to know about that because it's provided the relevant pages, the indices, and so it can navigate the memory that way. Um,
yeah. And also the KV cache needs to know it too, right?
exactly.
And that is maybe also one of the one of the things here that KV cache and attention with things like page detention, they become very, very much intertwined. And so, to my mind, it would almost make sense to have the attention function be part of this KV cache
Yeah.
module, right?
Yeah, for sure. You cannot do one without the other, and it's the place where, if you think about it, if you have a web server in front of all this, the routing logic, or if you have multiple machines, the routing logic needs to know where what is the machine that is more likely to contain a KV cache that is warmer for the current request, which is typically, if I'm directing requests with a different prefix in different machines, all those machines will need to pre-fill everything as opposed to finding things that are already warm in the KV cache. And so the attention in KV cache is where, and we were mentioning it the last time, is where all the layers of the stack are being pierced by the whole thing, and by the need of not consuming too much memory, to managing not doing too much compute. And this is actually where different frameworks decide to do things differently, but where you gain a lot of speed in in serving these models. And then you have the continuous batch inside of it, which is like, of course, also a factor where you want to say, okay, I cannot pre-fill and then wait to decode everything. I need to do a pre-fill in chunks, probably, because I cannot stop the world and pre-fill while the others are waiting for the next token. And so there's another dimension there where the pre-fill will populate the KV cache for a certain amount of generations, and you have different requests in the same batch, that one is at the first token, the other one is at the last token. And so if you don't go back and pre-fill at least a chunk of things, certain requests basically during decode will be empty. Certain batch entries will be
Right.
empty. So you want to handle that properly. And then there's also the question of whether you can devote some machines at prefill and some machines at decoding by moving the KV cache around or having a KV cache store, or whether it's better just to chunk prefill and you're done. So it's fascinating because all these things have a big influence on the performance of your system. And it's not just that there's a fixed recipe, right? Because depending on the application, you may have to make different, very different choices. For example, if you have I don't know, a routing model in a recommender system, you have a giant context that describes my preferences when I go on Amazon, and then they just need to suggest a few items. That's it for me to see, and there cannot be like 3 million. It's just 10, right? And so it's just so the decoding part from my inference will be very short, but the prefill will be giant. So in those systems, you tend to make certain decisions that you won't make in other cases where I need to chat with the model, and my my prompt, yeah, there will be a system prompt, but other than that, everything will be pretty lean. But I keep adding pieces to the conversation, and so I need to be directed to the same machine. And so it's very fascinating because this has become a whole industry. People that can make the right calls here are the people who will deliver better systems. And so I think thinking in from first principles, how the sausage is made in all these things is the only way to get to the other side. That there's no other way but to understand exactly how things flow throughout the
Yeah.
stack.
So fascinating KV cache stuff coming
Yeah,
along.
we started from something very tiny. Okay, Vikash, I heard about it, and now it's like if you can do this right, you can like get millions a month just by doing that. By doing that correctly.
Yeah.
I'm kidding, but not entirely, right?
Yeah.
So,
AGI will be determined by who has the best KV cache.
well, unless somebody comes up with diffusion models or some other trickery where, it's, well, sorry guys, it's not auto-regressive anymore. We don't care about the KV cache. It's all compute bound. We're not memory bound anymore.
Yeah.
And everybody can retire. So it's better to apply these things now and not next year. Anyway, it was fun. I'm
Yeah.
happy we managed to do it.
Super good.
Uh,
So you have a good vacation at the lake.
Absolutely, I will. And
Um,
you keep hammering on the keyboard.
yeah.
Bye,
Super good.
Thomas.
See you.